Let's work on solving some graphing problems. It's important for many applications of Calc 2 to know how to graph some of these very important functions. So first of all, let's graph y equals x. Graph of y equals x is a line passing through the origin with a slope of 1. It looks like this. There's the graph of y equals x. Y equals 3x minus 2. We have a y-intercept of -2 and a slope of 3. That means that when we have a rise of 3, we'll have a run over of 1. So this will pass through this point as well, 1, 1. That would go up 3 over 1. The line looks something like this. We have a y-intercept of -2 and a slope of 3. That's the graph y equals 3x minus 2. We should be able to graph any linear function that we're given. Y equals x squared is a parabola. It's important to know the graph of this as well. Looks something like this. We don't have to be really artistic with the graphs. We just have to know roughly what the pictures look like and to be able to give a quick sketch. For example 4, we have y equals the square root of x. Y equals the square root of x looks like the parabola, but sideways, and because x can only be positive, and the result of the square root of x is positive, we only have half of the parabola. So it looks like this. It should look like half of the parabola turned sideways. Let's look at the graph of y equals e to the x. It's very important to know this graph. We should be able to give a rough sketch of it. This is a very crucial graph that we should know. This is an exponential function, so the graph should sort of make sense if we know about exponential growth. It looks like this, and this point here is the point x equals 0, y equals 1. We must be able to give a quick sketch of this function and understand what that graph looks like. The natural log function is the same graph as this, but reflected across the line y equals x. So if we think of the graph of e to the x, think of reflecting it across the line y equals x. It looks something like that. That's the graph of natural log. There's a rough picture of natural log of x. This point is y equals 1, x equals 1, y equals 0. These graphs will also help us to figure out important values of exponential and trig functions. E to the 0, for instance, equals 1 because the graph passes through this point. The natural log of 1 equals 0 for the same reason. Let's look at a couple more graphs. The graph of y equals 1 over x looks like this. This will also help us to determine values of 1 over x with limits. For instance, as x goes to infinity, 1 over x goes to 0. As x goes to 0, 1 over x goes either to negative infinity or to positive infinity. The limit at 0 does not actually exist. For sine, we don't have to have a really pretty looking picture, just a rough sketch of what it looks like. Something like this. This value is x equals pi. This would be the value x equals 2 pi. And in the middle here, we have x equals pi over 2. It's important to know that the sine function never goes above y equals 1 and never goes below y equals -1. Cosine is also an important function to know the graph of. And it looks like sine, it's just shifted over. Something like this. So it's important to know the graphs of sine and cosine. Let's talk briefly about translations and stretches. We want to graph 3 variations of parabolas. Our base parabola is the function y equals x squared, and we want to graph each of these variations and see how different operations on x squared affect what the graph looks like. So let's first graph y equals x squared. Y equals x squared looks something like that. And let's talk about these different shifts and stretches, etc. 1 minus x squared. The 1 here is going to shift everything up a distance of 1 in the y direction. We're adding 1, but then we have minus x squared. The minus flips the graph over, so it's going to be flipped over and vertically shifted by 1. So 1 minus x squared looks something like this. That's not a great picture, but that's a rough sketch to show what 1 minus x squared looks like. How about y equals parentheses x minus 1? When we change in parentheses, that gives us a horizontal shift. So we're subtracting 1 in the parentheses. This is a bit counterintuitive, but subtracting gives us a positive horizontal shift. So x minus 1 is going to give us a shift in the positive x direction for the same parabola. So we're essentially taking the same parabola and just shifting it once in the x direction. That would look something like this. This would be y equals x minus 1 squared. Just horizontally shifted once, a distance of 1 in the x direction. How about this last parabola, y equals 2x squared? That simply takes the parabola and it stretches it out. So it will look a little bit narrower. Y equals 2x squared looks something like this. It's important to know what some of these basic horizontal and vertical shifts and stretches will do to a graph. Now let's talk about some important values of trig functions and exponential and log functions. E to the 0, as we saw just a bit ago when we graphed it, is equal to 1. Natural log of 1 is equal to 0. Natural log of e equals 1. We can determine these if we look at the graphs of the functions. For example, as we just graphed, e to the x looks something like this. When x equals 0, the y value is 1. That's why e to the 0 is 1. The natural log function is the same sort of a picture, it's just reflected across the line y equals x. So natural log of 1, that's right here, that is 0. Natural log of e is somewhere over here. This would be x equals e, and the natural log of e equals 1. That's because the natural log of e to the x is just equal to the x. Natural log of e to the x equals x. Also, e raised to the natural log of x equals x, because the exponential function and the log function are inverses of each other. Let's take a look at some important values of trig functions. We want to figure out sine and cosine for these three angles. We really should know the entire unit circle, but these are probably the most important and the most common angles that we'll use. And we're going to use this important sine squared plus cosine squared equals 1 to find an identity relating tangent squared and secant squared. So, in order to find sine and cosine for these angles, we could consider the unit circle. Here is an angle of 0, which is coterminal with 2 pi, as far as angles go. This angle is pi over 2. This angle is pi, 3 pi over 2 here, etc. When we take a particular angle and find a point on the unit circle means that it has a radius of 1. This is some angle, we'll call this angle theta. The point here has an x value of cosine and a y value of sine. So the xy point is cosine of theta, sine of theta. That means that this vertical height here is sine of theta, and this horizontal height here is cosine of theta. And notice that we have a right triangle. If we look at this triangle here, it's a right triangle with one side length of cosine, another side length of sine, and a hypotenuse of 1. If we use the Pythagorean theorem, side squared plus side squared equals hypotenuse squared, then we have this identity, sine squared plus cosine squared equals 1. That's an important identity that we'll use to find a related identity in just a second. All right, back to the unit circle. If we want to find sine and cosine for any angle, we can look at the corresponding point on the unit circle. With an angle of 0, the x distance here is 1. So cosine of 0 is 1. Sine of 0 is 0. How about pi over 2? Here's an angle of pi over 2. Here the cosine, the x value is 0, and the y value is 1. That means that cosine of pi over 2 equals 0. Sine of pi over 2 equals 1. And finally, let's look at sine and cosine when theta equals pi, when the angle equals pi. So that would be this angle here. Here the vertical height is 0, and the horizontal is -1. So cosine of pi equals -1. Sine of pi equals 0. We should at least know these values for sine and cosine, and really it'd be good to be comfortable with the entire unit circle as we begin Calc 2. Now, let's use sine squared plus cosine squared equals 1 to find an identity for tangent squared and secant squared. And here's how we're going to do it. Let's write down the original identity, and we're going to divide both sides by cosine squared of x. Since we are adding here in the numerator, we can split this fraction into two separate fractions. This simplifies to sine squared of x over cosine squared of x plus cosine squared of x divided by cosine squared of x. And this equals 1 over cosine squared of x. 1 over cosine is the same as secant. So 1 over cosine squared is secant squared. Cosine squared over cosine squared is just a fancy way of writing 1. And sine squared over cosine squared, well, we know that sine over cosine is tangent. So sine squared over cosine squared is just tangent squared. So here we have an identity that relates tangent squared and secant squared, and it's all based on this Pythagorean identity, sine squared plus cosine squared equals 1. And this really comes from the unit circle.